Welcome back. This video is section 5.3 and it's the part 3. It's the last video we're going to do on rational functions. So what we're going to look at today are 3 homework-like problems. Find the x-intercepts, y-intercepts, and horizontal and vertical asymptotes for this rational function. So we're asked to find 4 different things. The easiest one to find is horizontal asymptotes, so we're going to start there. To find the horizontal asymptotes, remember that we want to look at leading terms, because those are the terms that dominate as x goes to plus and minus infinity. So we'll look at leading terms. This is definitely a rational function. We've got a quadratic over another quadratic, and the leading terms, the ones that are really going to dictate how the function behaves as x gets bigger and bigger and bigger, are these first 2. So we look at the expression y equals 3x squared over 2x squared. How does this behave? These 2 variables cancel, and we get y equals 3/2. So y equals 3/2 is going to be the horizontal asymptote. That's what the function will tend towards as x gets larger, both positively and negatively. The next easiest thing to find is probably the y-intercepts. And remember, to find the y-intercepts, we set x equal to 0. That's true of any function. It doesn't have to be a rational function. So y-intercepts, we're just going to plug 0 in for x in this function. So f of 0 equals 3 times 0 squared minus 15 times 0 plus 18. 2 times 0 squared minus 18. This is 0, this is 0, this is 0, so we get 18 over negative 18, which is negative 1. So when y equals negative 1, and we already said that x was going to be 0, your y-intercept is where the function hits the y-axis, the vertical axis. And so any point on the y-axis, the x-coordinate is 0. So 0, negative 1 is our y-intercept. Let's see, we have 2 things left to find, the vertical asymptotes and the x-intercepts. Let's do the vertical asymptotes next. Vertical asymptotes, these are these vertical lines that the function has to totally avoid, cannot touch. And they come up when we're answering the question, where is the denominator 0? This is because this is a big, cannot do in math. You can't have a denominator equal to 0. And so those places where it is equal to 0, we have to eliminate from the domain. And often eliminating them from the domain results in these vertical asymptotes. We're going to start by looking at the function. We're going to factor as much as we can, both the top and the bottom. The bottom is what we're really interested in answering, where it's 0, but the top is important too, because we have to be able to distinguish between a vertical asymptote and a hole or a removable discontinuity. So let's try to factor this. The numerator, as I look at these 3 terms, I see that there's a 3 common to each of them, so I first pull that out. 3 times x squared minus 5x plus 6. On the bottom, it looks like there's a 2 common to both terms, so I'm going to pull that out. X squared minus 9. And now I'm left with some quadratics to factor, and I'll just try to factor these into 2 binomials. Let's see, this would be x and x, multiply to 6, add up to negative 5, x squared minus 3x minus 2x plus 6. That looks good. Okay, this is the difference of two perfect squares. And so it always factors the same. This will be x plus 3, x minus 3. Everything's factored, so I can start figuring out where my vertical asymptotes are. Right off the bat, I notice that there's this common factor in the numerator and the denominator. This will not result in a vertical asymptote. This, we've talked about before, is a removable discontinuity. Or a hole. And so they don't ask about those. They don't ask about removable discontinuities, so we just kind of leave that alone. This will not be allowed in the domain. You know, x could not equal 3, but it's not a vertical asymptote. This guy, however, has no one to cancel with. He's going to stick around for the long haul. So we know that there will be a vertical asymptote coming out of this expression. If x plus 3 does equal 0, that means x equaled negative 3. So this is not allowed. This is where our vertical asymptote will be. We get a vertical asymptote at x equals negative 3. And they don't ask for it, but we will get a hole at x equals 3. Okay, last guy is our x-intercept. So x-intercept, this means where does the function hit the x-axis? And that will happen whenever y equals 0. So we set y equal to 0 and solve for x. F of x is another way to describe y, so this is what we'll set equal to 0. So 0 equals, well, we already factored it, so let's use the factored form. 3 times x minus 2, x minus 3, over 2, x plus 3, x minus 3. Okay. For this whole expression to equal 0, essentially just the numerator has to equal 0. That's true of any fraction or ratio, that as long as the denominator is not 0, it is a 0, the whole expression is 0 if the numerator is 0. So here we have to answer the question, where is the numerator equal to 0? So where is this guy equal to 0? Where does 3 times x minus 2, x minus 3 equal 0? We have essentially three things being multiplied together. This cannot produce the 0. But maybe x minus 2 equals 0, which would say x equals 2. Or maybe x minus 3 equals 0. Maybe this is where the 0 is created. These will both produce a 0 in the numerator. This one we have to eliminate because x equals 3 isn't even allowed in the domain of the function. Because up here we saw that it would produce a 0 in the denominator. So this guy is off the table. He's not going to be an x-intercept because he's not even allowed in the function. So this right here is our only, not him, right here. This is our only x-intercept. So x equals 2 is our x-intercept. So one thing you can do is go ahead and graph this function and see if all of our conclusions are right. Here's our second homework-like problem. Sketch a possible graph for the function described. The function f has one vertical asymptote at x equals negative 2, a horizontal asymptote at y equals 2. The graph has a horizontal intercept at 4, 0, vertical intercept at 0, negative 6. It's concave down for negative 2 is less than x is less than 4 and has an inflection point at 6, 1. There's a lot of possible answers, but all we have to do is come up with one of them. So we're going to sketch a graph that meets all of these conditions. The function has one vertical asymptote at x equals -2. So we'll draw this dotted line. It's not part of the graph, but we know it's a vertical asymptote that we have to avoid in our graph, and a horizontal asymptote at y equals 2. So this horizontal asymptote will tell us how the function behaves as it's going off to plus and minus infinity. The graph has a horizontal intercept at 4, 0. 1, 2, 3, 4. So right here, the graph hits the x-axis. And a vertical intercept at 0, -6. 1, 2, 3, 4, 5, 6. The graph is concave down when x is between -2 and 4. Okay, and it has an inflection point at 6, 1. So 6, 1, right here we get an inflection point. And we know it's concave down in here. Okay, so we have to draw a graph that meets all these conditions. Well, let's start with the part in here that's concave down from -2, and we know that it has to approach that. It's concave down, and it's just going to go off to -infinity, never crossing this vertical axis, but getting closer and closer to it. At this point, they don't tell us what the concavity is between here and here. They just say this definitely has to be some inflection point. So I'm actually going to extend it concave down. And this is where it has to change to concave up because it's an inflection point and the concavity changes. So we're concave down, and then this inflection point, the concavity changes to concave up. But we do have to approach this horizontal line as x goes out to infinity. So I got to bring it back down. I could do something like this. And then as far as this side over here, they don't give us many clues, so we get to choose what we want it to look like. We'll make it look pretty simple. Maybe something like this. Okay, let's check everything out. Has one vertical asymptote at x equals -2. Yep, that's a vertical asymptote because this function is going to totally miss this vertical line. A horizontal asymptote at y equals 2. Okay, as x goes to infinity, the graph definitely is approaching y equals 2. As it goes to -infinity, it definitely is approaching y equals 2. It's okay that it crosses right here, horizontal asymptotes. The function can do that. It's just what's happening at plus and minus infinity. The graph has a horizontal intercept at 4, 0. Check. And a vertical intercept at 0, -6. The graph is concave down from x equals -2 to 4. It's actually concave down a little further. They didn't say there was any problem with that, so we're going to do that, extend it. And the inflection point, it definitely changes concavity right here. It goes concave up. And then we had to bring it back down so that it would still have a horizontal asymptote at y equals. All right, this is our last problem in section 5.3, a homework example like problem. And this will close out all our discussion on rational functions. In 1992, the National Highway Traffic Safety Administration recommended that states adopt 0.08% blood alcohol concentration as a legal measure of drunk driving. I don't know if that's true anymore. I don't know what the level is right now. A regular 12-ounce beer is 5% alcohol by volume, and the normal bloodstream contains 5 liters, 169 ounces of fluid. A person's maximum blood alcohol concentration, C%, can be approximately modeled by the multivariable function where N is the number of beers consumed in 1 hour and W is a person's body weight in pounds. Okay, at this point I'm going to pause for a minute and tell you that if you do in section 5.3 in the textbook that you can find on WebAssign, if you do number 2 and handwrite it on a piece of paper, all your work in the solution, you can have 3 extra credit homework points. Just take a photo of that number 2 and 5.3 and send it to me through Canvas messages. Okay, this is the important, back to the problem. This is the important function that we're going to use. And honestly, a lot of this stuff in here is just extra info. They've given us the function, and this is what we'll use. According to this model, how many beers can a person have and legally drive if the person weighs 200 pounds, 110 pounds? So how many beers, which variable is that? Is that C, N, or W? This was weight. This was the number of beers. So what is N when somebody weighs 200 pounds? So when W equals 200, or when W equals 110. We'll answer this question first. So legally drive, we have to be under this 0.08%. So we'll find out when does it equal 0.08%, and we'll know that we need to stay under that. So 0.08, when does 0.08 equal 600 times N, we don't know the N, over, let's see, W is going to be this 200. And then all of this, 169 plus 0.6 N. This is the equation, and we're really interested in knowing what N is, so we just have to solve this for N. Let's see, our strategy is we're going to collect all the terms with an N together, everything else on the other side, and then we'll be able to solve for N. So my first step is I'm going to multiply both sides by this whole denominator. So 0.08 times this denominator is 200 times 169 plus 0.6 N equals 600 N, and I multiplied the right side by the denominator, so it actually went away. It canceled. Another way you can think of this is just cross multiplying, either way. Okay, so at this point I have this times this times this, and I'm going to combine these two together first. So 0.08 times 200 is 16 times 169 plus 0.6 N equals 600 N. And then I will just distribute that 16. 16 times 169 is 2704. 16 times 0.6 is 9.6 N equals 600 N. Subtract 9.6 N from both sides. And I get 2704 equals 590.4. Good. That's totally solvable. We'll just divide both sides by 590.4. And I'll find out that N is about 4.579, about 4.6. So if you're 200 pounds, you need to stay, according to this model, N equals 4.6 beers is definitely what you want to stay under. Let's answer the question for the 110 pound person. Totally similar strategy, process. We just replace some, the only number we replace is this W right here. I guess I shouldn't skip that step. Okay, so using this formula, we know that we want 0.08 to equal 600 N over the weight is 110 now. 169 plus 0.6 n. We're going to solve this equation for n using the same steps that we did here. We'll multiply both sides by this denominator. And so on the left side we get 0.08 times 110 times 169 plus 0.6 n equals 600 n. We essentially multiplied the left side by that big denominator and the right side by this big denominator, and it canceled on the right side. Okay, multiplying this through, just similar, we have these three expressions being multiplied together, so I'll find out what 0.08 times 110 is, and it's 8.8. 8.8 times 169 plus... now I'll distribute the 8.8 through. 8.8 times 169 will be that number, and at the same time I'll just do 8.8 times 0.6. So I get 1487.2 plus 5.28 n equals 600 n. Subtract this so that we can collect all the terms with n's in them. And I have 1487.2. Whoops. 600 minus 5.28 is 594.72 n. Last thing to do to solve for n is divide both sides by 594.72. And then we find out that n is about 2.500, so about 2.5. So for a 110-pound person, you would want to stay under 2.5 beers. This was the 110-pound person on this side, and over here we had the 200-pound person. This is the limit. If you go above that, you're likely to be above the blood alcohol concentration. There's one more question we want to answer here. Does a person's weight have any impact on the upper limit of beers that can be consumed legally? Absolutely. Part A just showed that a 200-pound person gets to 0.08% blood alcohol concentration after 4.6 beers. This is all according to the model. We have to assume that that's correct. And a 110-pound person gets to 0.08% blood alcohol concentration after 2.5 beers. All right, you have everything you need to finish the homework on 5.3.